We're going to continue our conversation and talk about sequences specifically. The last section we looked at sequences and series. We'll focus just specifically on sequences on this particular section. Now remember, a sequence was basically a list of numbers. There was usually a rule associated with the numbers. And what we want to do is we want to talk about specifically the limit of a sequence. Now the reason we want to talk about a limit of a sequence is we want to get an idea of what the terms are going toward. Now the limit of a sequence do relate to the limit laws that we've learned previously in calculus. So we'll kind of bring up both of these topics. So to start off with, the curly brace notation represents a sequence. This particular sequence starts at 0 and goes to infinity. And so that's kind of telling me what the terms of the sequence are. The function that produces the sequence that I would like to look at right now is 1 over n plus 2, starting at 0 and going toward infinity. Now as a side note, a lot of times this value, this n equals 0 right here, it's not given because we don't really care what's going on at the beginning of a sequence. We usually like to see what's going on at the tail of the sequence, and sometimes this is why the initial value of these indices sometimes isn't given, but not all the time. Sometimes you will see it, but if you don't see it, don't be overly concerned because we're used to really focusing on what's going on at the end, the tail end of the sequence. So if we were to write out these terms, if we were to plug in 0, 0 plus 2 is 2, so this would be 1/2, and then I'd plug in a 1, 1 plus 2 is 3, so I'd have 1/2, 1/3, 1/4, 1/5, 1/6, 1/7. I think you kind of get the idea of what this sequence looks like. I could talk about many different characteristics of this sequence. First of all, they're all positive terms. Another thing I noticed about this is the largest that this ever was, this largest value in this particular sequence is a half. So this is bounded above. In this particular case, it's bounded above by a half. Now I kind of think that it might be bounded below too, but we'll have to figure out what that value is. So bounded above by a half, all positive terms. Another thing I notice about this is constantly decreasing. It's always getting smaller. Now this behavior we're going to learn is called monotonic. So it's monotonic decreasing. Now as this gets smaller and smaller, eventually I'll have 1 over 100, 1 over 1,000, 1 over 1,000,000. I think that this will be bounded below by 0. Now I'm never going to reach 0, but I'm going to get very, very close to 0 and not quite touch 0. So this characteristic, the characteristics of this particular sequence are it's bounded above and below. It's constantly decreasing, so we call it monotonic decreasing, and it has all positive terms. Now if we talk about this sequence, we can see that the sequence converges to 0. So if we talk about the limit, and we're going to have to come up with some new rules to be able to do this. If we talk about the limit as n approaches infinity of 1 over n plus 2, remember n are integer values like 1, 2, 3. We don't have any rules to associate this with the real numbers. But there is this nice little theorem, and I think in this book it's theorem 9.1 or something like that. And I'm not interested in memorizing the number because it's in another book it'll be another theorem number. But I want you to know that there's a theorem associated with taking these from the integers to the real number system and saying, you know what, I can change this n to an x, a real number, and I can take the limit as x approaches infinity of 1 over x plus 2. So now I've taken this from a non-continuous function to a continuous function. I know that this is going to be equal to 0, and I need to have a reason why, because the degree in the numerator is less than the degree in the denominator. Those are my shortcut rules. So this has a limiting value of 0. So as these values of n get larger and larger and larger, the terms of the sequence get closer and closer to 0. So the sequence converges. It's going toward a particular value, and in this case its limit is 0. Now if we were to graph this, first of all it's hard to graph such small numbers, but we could look at this and we could say, okay, it's starting at a half, so we could say that here's a half, and as n equals 0, it started right here at a half, and n equal 1, I was down here at a third, and is n equal 2, 3, 4, 5, 6, 7, 8, you can see that it's getting closer and closer and closer to 0. So this kind of pictorially gives that same information. So the limit of the sequence changes from the limit of a function by this theorem. You should always note that there's a theorem there. I guess I don't care so much that you know its name because it changes based on the book that you're in. Now all the rules that we learned about limits apply to the limits of a sequence as well. So the limit of a sum is the sum of the limits, the limit of a product is the product of the limits, all of those neat things. So that's not really any new information. The new information is talking about these in terms of a sequence. So let's go ahead and determine the limits of the following sequences. Now remember, we take this idea and we're looking at integer values for a sequence. So I would like to figure out the limit as n approaches infinity. Let's do 4n cubed over 2n cubed plus 4. And I can say, you know what, there's this theorem that says I can take the limit of a sequence and change it into the limit of the same function using real numbers, and this matters. So I'll be looking for this idea of changing it from integer values to real number values. And when I take this, I get 4 over 2, which is 2. And I need a reason why, and the reason why is the shortcut is the degree in the numerator and the degree in the denominator are the same. Therefore, the limit is the ratio of the leading coefficient. Now, because we have a particular limit of a constant here, this tells me that this also converges. So the terms of the sequence converge. Let's look at another one. The limit as n approaches, actually this should be infinity up here. I don't know if it got erased or it was never in there. So the limit as n approaches infinity. Let's look at 5n squared over 12n to the 5th minus 7. Now for this one, I'm going to say the same thing. There's this theorem that lets me take these from integer values to real numbers. So this is the limit as x approaches infinity of 5x squared over 12x to the 5th minus 7. This is equal to 0, and we need to have a reason why, because the degree in the numerator is less than the degree in the denominator, so this converges as well. Now if you don't remember the shortcut rules, you can go through and divide through by the highest power of the exponent in the denominator. That was where these rules came from back in Calc 1. Let's look at another one. Let's look at the limit as n approaches infinity. Let's look at 2n to the 5th over n minus 1. Now this one, I use that same idea of the theorem to take it from integers to real number values. So I'm looking at x approaches infinity of 2x to the 5th over x minus 1. This is equal to infinity because the degree in the numerator is greater than the degree in the denominator. Both the numerator and the denominator are going toward infinity, but the numerator is going faster because it has the higher power. So that means that this one diverges. The terms are getting larger and larger in this particular sequence. Now a really interesting one that we can look at has variables in the exponent. So let's look at the limit as n approaches infinity of n minus 2 all over n to the n. Okay? Now if we go ahead and rewrite this using x's, because remember n are integers, we want to go ahead and rewrite this using x's. X approaches infinity, x minus 2 over x all to the n. If I look at the inside portion here, if I look at the degree in the numerator and the degree in the denominator being the same, this inside portion, that's an x up here, I'm thinking this goes to 1. So this is 1 to the infinity. That's an indeterminate form. It's not indeterminate L'Hopital's, but it's indeterminate. So let's go ahead and try and rewrite this. One thing we could do is we could separate the numerator. You can always separate the numerator, you can never separate the denominator. So let's go ahead and rewrite what we'd have here then. X over x is 1 minus 2 over x to the x. I keep writing n, but this should be an x. So this piece, the 1, the limit of a constant is just this constant. So I'm going to have 1 minus, as x goes toward infinity, this term goes to 0. So 1 minus 0 to the infinity basically is still another 1 to the infinity, which is indeterminate. Okay, so that means I'm going to have to use a rule here. Now this is going to be similar to logarithmic differentiation. If you remember with logarithmic differentiation, I had a variable in the exponent and I wanted that variable to come out front. So that we took a natural log of both sides. So the first thing I need to do is I need to rewrite this so it has two sides, because right now it only has the one side. So this would be 1 minus 2 over x to the x. And I'll go ahead and take the natural log of both sides. Now the reason we're taking the natural log is this exponent. We want to pop it out front, and we'll show this step by step. So the log of the limit is the same as the limit of the logs. So I'm going to pull this limit out front, and then this x that's in the exponent I will pull out in front of the log. And here I'm done then with this rewrite, and see what we get. So as I plug infinity in, or if I take the limit as x approaches infinity, I get infinity. And then this piece, this goes to 0 and the natural log of 1 is 0. So this is infinity times 0, which is indeterminate still. So I need to do another rewrite. I need to get this with a numerator and a denominator, and if I have that numerator and denominator, then I think that I can get this into an indeterminate L'Hopital's form. So this is going to be my numerator. Now this x I want to pop down into the denominator, and the way I'll do that is I'll divide by 1 over x. So I'm trying to multiply by x. Multiplying by x is the same as dividing by 1 over x. Now as I take this limit, this denominator goes to 0. The numerator, 2 over x, goes to 0. 1 minus 0 is 1, and the natural log of 1 is 0. So this is now indeterminate, but more important, it's indeterminate L'Hopital's. Now we've looked at indeterminate L'Hopital's before. Don't drop the left-hand side here. I need to take the derivative of the numerator and the derivative of the denominator. So the derivative of the natural log of u is 1 over u times the derivative of u. And then of course I need the derivative of the denominator as well. So I still didn't take the actual derivatives yet, so let's go do that in my next step. So the derivative of negative 2 over x, that's the same as negative 2x to the negative 1. So I'd bring the negative 1 out front. Negative 1 times negative 2 is 2. Decrease the exponent by 1. Down here, this is the same as x to the negative 1, so I'd bring the negative 1 out front, decrease the exponent by 1. And we can see that we have a lot that cancels here. The x to the negative 2's cancel. Put that in a different color. Leaving the 2, of course, and leaving the negative sign. And I'm left with the natural log of y equals the limit as x approaches infinity. Okay, so we have a 2 and we have a negative, so it looks like to me I have a negative 2, 1 over 1 minus 2 over x. Now as x goes toward infinity, this piece goes towards 0. 1 divided by 1 is 1. 1 times negative 2 is negative 2. And I'm left with the natural log of y equals negative 2. Well, remember, natural log of y is the same as log base e of y equals negative 2. Rewriting this in exponential form, I get e to the negative 2 equal y, or my answer is y equal e to the negative 2, or 1 over e squared. So we kind of have to remember what we're even doing here. We were trying to figure out whether this converges or diverges, basically. So when we're starting way back up here, we wanted to take the limit and we wanted to know if it converged or diverged. So we found the limit, so therefore the limit of that expression is 1 over e squared. This implies that the terms of the sequence converge, meaning they're getting closer and closer to 1 over e squared. So this is a big idea. You're going to use this quite a bit in this particular assignment, this idea of rewriting. In this idea of multiplying by x is the same as dividing by 1 over x will come up quite a bit. So make sure that you're kind of looking out for that, because that's definitely one that will show up in your handwritten problems that you submit for homework, and one that will show up on your exam. So knowing those details on how to do that will be very important. Now we talked about some terminology for sequences up above, like monotonic and increasing. Let's go ahead and look at some specifics. The first one I want to look at is increasing. Now all of these have formal mathematical definitions. We'll look at those, but we'll also just look at some sequences that look like they're increasing. So for instance, this sequence is increasing by a half each time. Okay, it's never staying the same. I never have a repeated value. It's always getting larger. So the way we talk about this is a sub n plus 1 is greater than a sub n. So this basically means the next term is greater than your current term. The next term is larger than the previous term. It's always increasing. It's always getting larger. So along with that, we would have an idea of what as well about non-increasing or decreasing or non-decreasing. We'd have all those different options. Let's look at decreasing next. We'll look at the two easiest ones first. So decreasing would be something like 0, -1, -2, -3. It's always getting smaller when it's decreasing. So what this means is the next term is always less than the current term. So the next is always less than the current. Now the trickier ones are when we talk about non-increasing and non-decreasing. Basically we have to avoid a repetitive value, meaning you see the same value twice. So let's go ahead and look at non-increasing. So for non-increasing, let's look at a sequence. So for instance, something like 0, -1, -1, -2, -2, something like that. So if you notice, it's decreasing, but it's also repeating. So from -1 to -1, it's staying the same and it's not decreasing anymore. So it kind of has a mixture of a lot of things that are going on here. So what we want to say here then for non-increasing is the next term is always less than or equal to, because I have that equality here, than the current term. So the next is always less than or equal to the current term. So these are a little bit trickier to talk about non-increasing. Let's also look at non-decreasing. So if we talk about non-decreasing here, we can talk about something like 1, 1, 2, 2, 3, 3. So what we have then is a sub n plus 1, which is our next term, of course. Now if we look at this, it's always going to be greater than or equal to our current term. So next is greater than or equal to the current. So these ideas of increasing, decreasing, non-increasing, and non-decreasing are important after we add a couple more terms. The next term I want to talk about, we've looked at before, is monotonic. Now when I think about monotonic, I either think as always increasing or always decreasing, but we can also think about it as non-increasing and non-decreasing. I have the same behavior or the same pattern. It's either staying the same or getting larger, or staying the same or getting smaller. So either non-increasing or non-decreasing. It's not increasing and then decreasing or going positive, negative, positive, negative. Basically it's moving in one direction. Okay, last one. We've already talked about this one as well, but let's go ahead and add it to the list, and that's bounded. Now we talked about bounded above and bounded below when we were looking at some of the original first problems, but basically the formal definition says if there is some number, and we're going to call that number m in this particular case, such that the absolute value of our terms, because we could have a positive negative thing going on, or we could have an alternating sequence going on, is always less than or equal to this value for all values of n, then what we do is we call it bounded. So it never gets above or below a particular value, then it's bounded. So this is really important because there's a special theorem that goes with this. Now this theorem talks about the terms of a sequence, And basically it states that a bounded monotonic sequence and this will make sense when we see this, it converges. It's bounded, so it's going toward a particular value. It's monotonic, meaning it has the same behavior as increasing or decreasing. And so that makes sense when we talk about whether it's bounded, monotonic, and convergent. Let's go ahead and look at some particular toolbars. Sorry, that said toolbars, so I said toolbars. Let's go ahead and look at some particular problems where this could come into play. So for instance, we could have a sequence a sub n. Let's look at 2 minus 1 over n equals 0 to infinity. Let's go ahead and write out some terms. I think 1, 3/2, 5/3, 7/4. I think you get that pattern in the numerator, 1, 3, 5, 7, 9. Denominator is 2, 3, 4, 5. And this continues on. Now if I look at these in terms of mixed numbers, this would be 1 1/2, 1 2/5, 1 3/4. That's not 2/5, that's 2/3. 1 4/5. So if you notice, the 1 is the same thing. Now the fraction over here, the numerator is always 1 less than the denominator, so that means it's always going to be less than 1. But notice how it's getting closer and closer to 1. So if we talked about this, we would say that these terms are increasing. Okay, so that's important. It's monotonic. And in this particular case, they're getting larger and larger, so it's monotonic increasing. There's no repeated values. And it looks like to me that it's bounded above by the number 2, meaning I'm getting larger and larger and larger. I'm getting closer and closer to 2. So because it has all these characteristics, we would say that it converges. Okay, and so that's important, that idea of converging. That's something that we always look for. Now we can also have an alternating sequence or an alternating list of terms. Now a lot of times when we talk about the alternating sequence, a trig function is involved, like sine or cosine, because we know as we move through the quadrants, sine and cosine change whether they're positive or negative. So we could have an alternating sequence, and this one probably wouldn't be based on a trig function because it goes every other one. But we can see that it's going above and below, positive, negative, and it's getting closer and closer to a particular value. So this is an alternating sequence that converges to 0. We could also look at an alternating sequence that starts out and it diverges. It's getting larger and larger. So an alternating sequence doesn't always have to have convergent or divergent behavior. It depends on the particulars of that sequence. Now, a geometric sequence sometimes will produce an alternating sequence, but not always. A geometric sequence has some particular characteristics that are important to know. First of all, its general form, well, actually let's talk about how it's obtained. A geometric sequence is basically obtained by multiplying the previous term of a sequence by some fixed constant. So what's happening is every single term is always multiplied by the same value. It doesn't change. Now there's a couple different ways that you can write the form of a geometric series. The one that I am familiar with and I use the most, and that you'll see again when we talk about a series, is a times r to the n. Now notice just the r is raised to the n power, the a is some coefficient out front. Now when you have this fixed constant, I guess we could add some more detail here. This fixed constant is called the ratio. And this ratio we represent with r. And so that's what this value of r is down here then, is that ratio. Now a couple of different things are happening here. R cannot equal 0. A cannot equal 0, because if r and a were 0, this would not be a very interesting sequence. All the terms would be 0, and they can be any real number except 0. Now we have a couple things that happen here. It converges if this value of r is between -1 and +1. Now notice I have equality at 1, because if I have equality at 1, what ends up happening is this is 1 to any power is 1. And so my terms would be getting closer and closer, actually equaling 1. But if I have a -1, as my powers go even and odd, I produce an alternating sequence. So it depends on whether we have an equal sign here or not, so that's an important distinction. It diverges if r is greater than 1 or if r is less than or equal to a -1. So those are some important characteristics. And then we can also talk about the limit based on these. If I take the limit as n approaches infinity of r to the n, and I'm going to leave that a in there as well, I have a couple different things that can happen. It can go to 0, it can go to 1, or the limit cannot exist. We have these three options. If the limit is going to be equal to 0, this would happen if the absolute value of r was less than 1. The limit would equal to 1 if r was equal to 1. Not the absolute value of r, but just r is equal to 1. The limit wouldn't exist if r was less than or equal to a -1 or if r was greater than 1. And as we see some examples, these will make a lot more sense. A couple of other distinctions here. If r is greater than 0, that ratio, then what happens is a times r to the n is a monotonic sequence, meaning it has that same behavior. And in this case, monotonic sequence, whether it's increasing or decreasing will depend on whether r is a fraction or if it's greater than 1. If r is less than 0, then what ends up happening is it's going positive, negative based on the exponent being even or odd. So then a times r to the n oscillates, meaning it goes above and below the axes. Now this can happen a lot with a trig function like sine or cosine as well, so that's something to look out for. Now when we talk about trig functions, a lot of times what ends up happening is you'll have two positives and then two negatives if you're looking at like sines or cosines, but that's not always the case. So some examples that we could look at here would be something like the sequence of, let's look at 2 times 0.3 to the n. So this is definitely an a times r to the n, which again is a geometric sequence. So for this one, we want to figure out, does this converge or does it diverge? And if it does converge, what does it converge to? So if we look at this, we see that r is equal to 0.3. So if we look up above, let's see if I can get this to scroll. If we look up above, we can see that 0.3 is between -1 and 1. Except there's no equal sign here. Therefore, we would say it converges. And that's from right up here. And then second of all, what does it converge to? Well, we could see that the absolute value of r, so the absolute value of 0.3, is definitely less than 1. Therefore, the limit as n approaches infinity of 2 times 0.3 to the n would be going toward 1 is what we have here. And thus, for simplicity's sake, let's make this a 1 right here, because we haven't really learned to deal with anything other than a 1 for a coefficient there. So we just compare to those, and then we try and determine whether, if it's going to converge, what it converges to. In this particular case, the limit is 1. And that kind of gives us some information there. Now when we turn these into series, which will be our next sections that we look at, we'll be talking more about series than sequences, we'll be able to put an extra formula with this to determine what the partial sums are converging to as well. Now let's go ahead and look at growth rates of sequences. When I was learning calculus, I never learned these. We always had to do all of these by hand, so it was kind of interesting that they'd have this as a, I don't think it's a theorem in the book, but it's definitely interesting and good to know. So growth rates of sequences. Basically what we're doing here is we're talking about comparing what grows faster. So for instance, if we had something, let's say like 2 to the n over n factorial, they're both going toward infinity, but the question is which one is growing faster? I can't use L'Hopital's here, and the reason I can't use L'Hopital's is I can't take the derivative of n factorial. So I can't use L'Hopital's there. So what we have is we have a list. And the list basically tells you how fast they grow relative to each other. So if we had an expression like natural log of some power to the n, that would be growing slower, and the notation that they use is 2 less than signs. It just means growing slower if I had something like n to the p. So that would be growing slower than if I had something times n to the p natural log of r to the n, which grows slower than n to the p plus s. And the p that I can compare from here to here. So that's an important thing to distinguish. That would be growing slower than some number like 10 to the n, which would be growing slower than an n factorial, but growing the fastest of all would be an n to the n power. Now what ends up happening here is if you have something growing slower on the top than you do the bottom, it's going towards 0. If you have something growing faster on top than you do the bottom, it's going toward infinity and diverging. So this list is important. So how do we work with this list? We could look at a problem to determine what converges and what diverges. We could have something like the natural log of n to the 10th all over 0.0, we'll put a bunch of zeros in here, times n. Now, just as a quick side note as well, these rankings that we have here do not change if we just multiply by some positive coefficient out front. Okay, so let's go ahead and pop this 10 in the front first. So this would be 10 natural log of n all over 0.00001 times n. So what we're saying is this 10 and this 0.00001, that's not really affecting what my solution is. But what does affect the solution would be the ranking. So here we just have a plain old n, not very exciting. This would be an n to the p, which in this case would be an n to the 1. This is just a natural log of n. Now if you want to look at this q, that would be to the first power as well. So if we look at this natural log of q to the n, this is the slowest. This one, n to the first, is a little bit faster. So this is slower, this is faster. So they're both going toward infinity, but the denominator's overtaking the numerator in terms of size. So this is going towards 0. Because again, I have this ratio, and this is how I show it. Slower over faster, so it's going towards 0, which implies convergence. So knowing this list is very, very helpful, but you still need to compare the slower over faster, or vice versa with faster over slower to draw your other conclusion here. Let's go ahead and look at another one. Let's look at n to the 8th, natural log of n, all over n to the 8.001. Now this one, let's make sure we still have our rankings up here. This n to the 8th looks like this one right here. So this would be n to the 8th, natural log of n, and this would be to the power. So ln of n, let's say to the 5th, not just the n to the 5th, but the whole ln. And this would be n to the 8 plus 0.000, just 2 zeros, 1. So what I'm able to do then is I'm able to compare these. This would be n to the p plus, I think that was a q actually, p plus s, make sure we get this right, some other constant. So this would be n to the p plus s, so this is faster than this n to the p ln of n. So our fastest one is in the denominator, slower one is in the numerator. The overall fraction goes to 0 then because the denominator is increasing without bound, so this converges. Okay, and it's just that simple comparison off of that list. Let's look at another one. Let's look at n factorial over 10 to the n. Now if we look at our list, n factorial is going faster than 10 to the n. N to the n would be like a variable to a variable. B to the n is our 10 to the n piece here. This is going slower. They're both going toward infinity, but the numerator is going faster, so the overall ratio is going toward infinity, so this diverges. So knowing that the growth rate, the sequence of these, which grows fast versus slowest, is important, and it kind of makes things a little bit easier for you when you're comparing some of those and taking limits. Now the squeeze theorem can come into play here as well, and the squeeze theorem works the same in this section as it did in previous sections. So if you see anything that looks like it could be solved with the squeeze theorem, you're probably right. Let's go ahead and look at some problems that could or could not be a squeeze theorem, or maybe one of our shortcut rules. But let's look at the limit as n approaches infinity, and let's look at the inverse tangent of n over 18n. Now remember, we have this theorem that I can take this into the real number system, and I have the limit as x approaches infinity of the inverse tangent of x over 18x. Now when we look at this, the limit, remember the limit of a ratio is the ratio of the limits, meaning I can take the limit of both the numerator and denominator separately. So when I look at this, this numerator is going toward pi over 2. And if we want to know why, this is our what angle, and this is always important to justify. What angle in the interval from negative pi over 2 to pi over 2 approaches infinity? And of course that's going to be pi over 2 in this particular case. Now the denominator is getting larger and larger. It's increasing without bound. So I have a fixed numerator. I have a denominator increasing without bound. This is going towards 0. So this converges. Okay, so that idea is really important. Now this is definitely monotonic, because if you think about the tangent function, you know, I have this right here. So the tangent function, and I'm talking about what angle as it approaches infinity, has that constant behavior. And of course the arctan function looks a little different from this, but it's monotonic as well. And you can also see that it's bounded above by pi over 2. So it's bounded, it's monotonic, and if we have something that's bonded and monotonic, we know that it converges. In this particular case, it converges to 0. So these are all the different examples of, you know, different types of problems that you might run into. And it's important that you always be able to justify the behavior of these functions. Sometimes it helps to graph these, and on your handwritten homework, if you graph them to help figure out what's going on, make sure you include your graph to justify your work. On the exam, if that's appropriate, I'll include a graph to help you out, because I wouldn't expect that you know how to graph very many of these. And we can also be given a problem where we're asked to produce a sequence, and those are kind of some of the more interesting ones. So the problem I want to look at that you'll come across in your My Math Lab homework would be something about medication. So suppose the S with the P hanging from it means suppose. Suppose a person takes 90 milligrams of medication every 8 hours. Now the dosage is important here, this idea of every 8 hours. We're going to assume the half-life of the medication is 8 hours. So that means after 8 hours, half the medicine that was in your system 8 hours ago is gone and half is left. What we want to do is we want to find some sort of a relationship to describe the amount of drug that's in the blood after the nth dose. So let's go ahead and look at our initial dose. So with our initial dose, we know that we started with 90 milligrams. So 8 hours later, what ended up happening is I take another 90 milligrams, but I have half of the 90 that I'd already taken previously. So this would be 90 plus half of 90 is 45, as I'd have 135 milligrams in my system. Okay, after 16 hours, what would happen is I'd take another dose. And remember, I had the 45 milligrams from before, but I'm going to write it like this. I'm going to say that I had half of this 90 from before, plus I have another half of that 90. Okay, so let's look at this one more time. This is my initial amount. This was what was remaining after my first dose. This is what was remaining after my second dose, half of the 90. So 16, so if we do another 8 hours, we'd be at 24 hours. So take another dose, I have half of the 90, then I have half of the 90 from the previous dose, and then from here I have half of the 90. So if you want to think about this half of the 90, this is the same value each time, and then I just end up having it each time. Now what we're looking at here, if you want to actually go out and calculate these, which you'll want to, we'd have 157.5 here. So there's a big increase, 90 to 135, that's a big increase. 135 to 157.5, not such a big increase. And then as we look at our next one, you can tell it's starting to get closer and closer to a particular value. And it also looks like a geometric sequence. So if you look at this, remember a geometric sequence looked like a times r to the n. Well, a in this case is this constant that's the same. And then what happens is this value of r is the ratio I keep multiplying by. So I have 90 times half to the n. And for this particular case, I end up starting with n greater than or equal to 0. If n is 0, half to the 0 is 1, 1 times 90 is 90. That's my initial value. And then I kind of keep working through from here. And what we want to look at is what is the limit of this sequence. That's basically what we want to try and come up with. Let's go ahead and look at this in terms of dosage, I think is what they have us use. Here is dosage. So the next dose is equal to, and we have to find out some sort of a relationship here. It looks like to me I always started with the 90, and then I had half of the previous. So let's see if that works. So I have my 90 plus half of the previous. 90 plus half of the previous. 90 plus, and then if I combine these, it would end up being half of this previous as well. So once you simplify these, we can see that we do constantly get that half of the previous dose. So d sub n plus 1 is equal to 90, because that's my initial dosage, plus half of the previous dose. And then we could start talking about the limit of a sequence as we keep going through and simplifying this. Definitely going to need a calculator for something like this. I don't see that it's easy to take the limit of. But eventually what we'll see is this is partial sums. This is a sequence of partial sums. And in a subsequent section we'll see that what ends up happening here is this sum looks like a over 1 minus r. A in this case is 90, r is a half. So 90 over half is the same as 90 times 2 is 180 milligrams. So what that's saying is after the nth dose, the limit of the sequence is going toward 180 milligrams. So what we're looking at then is that would be kind of the amount that was going to be consistently in the blood if we kept taking our medication using that particular pattern and dosage limit. So that's kind of an interesting problem, and it really brings out the idea of a sequence, and it also brings out the idea of partial sums in a series, which, you know, technically we're not covering in this section, but it kind of makes it easier to work with. As usual, it's really important that you show all of your work. If you have questions, please let me know. You can shoot me a text. You can also use your Pearson Connects to a tutor or set up an online meeting as well. Good luck, and please let me know if you have questions.